Dear student, let us begin the lecture on machine design part 1. This is lecture number 18 and the topic is power screws. Now power screws are important device to transfer the rotational motions into the translational motions. Now you might have heard of the name rack and pinion drive, which serves the same purpose, that is, it converts the rotational to the translational and vice versa. But the important difference between the power screw and the rack and pinion drive is that in the power screw the axis of rotation and the direction of translations are collinear, whereas in rack and pinion drive the axis of rotation is orthogonal to the direction of translations. Now power screws were used even in antiquities since the days of Greeks, as we can see from the historical documents. They even named power screws as one of the 5 elements of machines. Even today power screws find importance in the machine design. Now let us look at the reasons behind so much wide applications of power screws drives. The first one is the large mechanical advantage. So this part, which we are going to explain in this lecture, is very important, that the machine must have a good mechanical advantage. Then the second is possibility of obtaining slow motions. Now this is also important because sometimes we need very slow movement, and with any other drives it may not be very much possible, but this is much possible in the power screw drive. It has high load capacity with small overall size. So that is again a very important factor. The machine should have a good load capacity, but it must be convenient in shape and size. Then the fourth point is highly accurate motion for adjustments. Sometimes we need very accurate motions. For example, in positioning instruments we need accurate adjustment of the motions. For example, in telescopes, to look at the stars, we need to get fine adjustment of the motions, and this is possible by power screws. Now it is very simple to design such power screws, and that is very important from today's point of view. The ease in manufacturing is of course there, as we have already known for the threaded fasteners, that it could be manufactured very easily by turning process or by rolling process. This is very important factor. So now we see the advantages of such power screw drives. Then let us look at the typical fields of applications of such power screws. Now it is used for raising load. You might have seen the screw jack, which is used in automobile industry to raise the automobile. Now screw jacks are very useful there. Then the second application is that loading specimens in testing machines. Again, the testing machines are used to load the members for various experimental purposes, and here you will see that the power screws find their applications. Then the third application is obtaining required motions in machining and press working. You might have seen the lathe machine, and there you might have also seen the lathe carriage, which carries the tool and it is given a feed motions. Now this feed motion is given to the tool by means of the power screws. Also it is useful in the press working operations. Then we require sometimes very precise indexing motions, and there power screws are very much applicable. Indexing motions are very important in designing and manufacturing certain things. For example, in gear manufacturing you see that indexing is very important, and if indexing is not perfect then the gear profile may be inaccurate, and that leads to inefficiency in the gear transmission. So indexing is very important thing, and the power screws could be useful there. Then providing motions of operating members of robots. These days robots are used, and to have the movement we use sometimes the power screws, because it is it has high load capacity, and it is small in size. Therefore, these are the typical fields of applications, but this is not exhaustive, and apart from this there are numerous other applications also possible. Now, come to the kinematic arrangements of screw and nut pair. Now, depending upon the fixation of the screw and nut, there are two members in a screw mechanism, screw power screw drive. One is screw and another is nut. Now, screws have thread cut on the external surface, whereas nuts have threads cut on the internal surface, internal side. Now, depending upon the fixation of the screw and nut, we may have three possibilities. One is the rotating screw and nut moving axially. That is, here the screw rotates and the nut moves axially. This is very common in use, and just now I have mentioned about the feed motions in lathe, and there you will find the screw rotates. Here we have the lead screw, which is known as lead screw, which rotates, and the nut moves forward, and this nut carries the tool holder which holds the tool. So, therefore, feed motion is given by this mechanism. Then the second category is the simultaneous axial and rotational motions of screw with fixed nut. Here the nut is held fixed and the screw moves as well as it rotates. Now, you might have seen the screw jack. Here the mechanism is just like that. We have the fixed nut and then the screw is rotated and it moves in the same direction of rotations. So, this is one arrangement. There may be arrangement where the rotating nut and screw traveling axially. It is just the reverse, that is, the nut rotates and the screw moves axially. Let us see. Here, suppose we have two threads, two screws. This is right handed, and let us say this is left handed. And we have a fixed nut here which is rotated. Rotational motion is given to the nut, and because of that the screw advances in the opposite directions and it gives a force in these two directions, T1 and T2. Now, this is important to give tension to cables, and this could be taken as a threaded fasteners. Here also the screw is traveling axially, but the nut is held fixed. This is known as the turnbuckle. Now, let us come to the basic thread types in power screws. In lecture 16, we mentioned about the different threads and the geometry of the threads in some more details, and there we have mentioned that in power screws the most frequently used threads are square or acme or trapezoidal thread or buttress thread. Now, let us look again at the main geometric parameters of such a thread. Now, here the square thread the geometry of the square thread is somewhere like this. Here the pitch is P and this length is P by 2 and this is again P by 2 and the height of the thread is P by 2. Now, what are the advantages? Advantage is that because of this surface which makes angle 90 degree, it is quite efficient, that is the frictional loss is less. But what are the disadvantages? Disadvantage is that the thread area is very small. So, of the entire pitch only p by 2 has some material. So, therefore, the strength of this screw is very small. And secondly, and that is very important, that it is difficult to machine. That is, it is, we will see that we need a good surface finish of the screw threads, and it is difficult to have a good surface finish for this kind of square thread. So, we now go to the next type, that is acme or trapezoidal thread. Here some of the difficulties are removed. The thread profile here looks like where again this is the pitch length, but this angle which is known as thread angle is taken to be 29 degree for acme thread, and for trapezoidal thread it is 30 degree. Then we have some of the advantages of this kind thread. That is, here we have of course large mechanical loss, that is large friction loss, but now it is possible or it is easy to machine this thread. And secondly, the root strength is quite high. So, the disadvantages of the square threads are now taken care of here in trapezoidal or acme thread. And in some machines where we need frequent engagement and disengagement of the screw and nut, then this is very useful. You will see that here this kind of square thread is not very useful for that purpose. Now, this kind of frequent engagement and disengagement are very common. You might have seen the lathe screw. In the lathe machines, of course, we have a spiral cam which is used for engaging and disengaging the nut with the screw, and there the acme thread is very much beneficial. Now, let us look at the buttress thread. Look at the buttress thread. Some of the advantages of the square thread as well as acme thread are now combined here. The thread profile is very much like this. This angle is very small, roughly taken to be 7 degree only for the ease of manufacturing, and this angle is quite large, about 45 degree. Now, you see the advantage is that here the frictional loss is very small, whereas the root strength is quite high. So, therefore, if we have a nut which is engaged here, then it is easy and efficient to transfer power from one direction, but the disadvantage is that it can transfer power only in one direction, and in reverse it is very much inefficient. So, these are the three common types of threads used for the power screws. Now, there are standards for the square threads as well as acme and buttress threads. The standard for square threads is tabulated, and the standard is named as IS 4694, and it was tabulated in 1968 and reaffirmed in 1983. In any machine design handbook, you will find such tables. Now, you should know how to read those tables. You will find different parameters mentioned there. One is the nominal diameter of the screw, and that is equal to the major diameter of the screw. Then we have the minor diameter of the bolt or the screw, and the minor diameter of the nut. We have the pitch, and we have the height of the thread for screw, height of the thread for the nut, and as well as the stress area, that is the smallest area at the root. Now, I urge that you must look at those tables and try to use those tables as often as possible. Now, we come to the kinematic and static analysis of the screw. Let me draw the basic geometry of the screw. Now it is a cylinder and we have the thread cut on this surface. Here this length is denoted by L, and this is the length by which the nut or screw advances, depending upon the which is fixed and which is movable, by the length L for a single turn. That is the movement for 2 pi revolution, for a single revolution, that is 2 pi radian is L, and this is known as the lead of the screw. Now this is also the pitch of the screw, because the thread is single thread. But now if we use another thread in the cut in the unthreaded region of the same cylinder, looks something like this, then the pitch length is this much. This is the pitch. Now this is multiple threaded screw and the pitch is here, and lead is equal to twice that of pitch. Now the general rule is that lead equal to n times pitch, where n is the number of threads. That is, in a multiple threaded screw, if there are n threads, then we have this relationship L equal to n times P. Now also you will see that as it is gradually wrapped up, so therefore there is an angle phi. And how to measure this angle? So if you rotate it by 1 revolutions, then if this diameter is, let us say, d of P, pitch diameter, then if you revolve by 2 pi, then this is pi times dP, and then the lead is L. Therefore this angle, which is constant angle, is equal to phi, let us say, and therefore we have tangent phi equal to L divided by pi dP, or L is pi dP tangent of phi. So this is the relationship. Now when it moves by 1 revolution, it advances by L. So therefore what will be the velocity of the axial velocity of this screw? Then definitely the axial velocity will be equal to L, which is per revolution, and if the number of revolutions per second is f, let us say the frequency, it is moved with frequency f, then the axial velocity is f times L. But now we see that whenever the screw moves, then this is the axial velocity, but the real velocity of the screw material is along their directions. And what is that? This will be equal to, if you see that V and this is VA, so therefore this is phi, and VA will be equal to V sin phi, and V equal to VA divided by sin phi. So phi is very small. Now you see that even if the axial velocity is very small, but the rubbing velocity is quite high, and that is very important because the depending upon the rubbing speed, the wear and tear takes place. So therefore, if the speed is quite high, then the wear may be very high, and that's why we should not have too much running speed of the machine. Okay. This is one of the disadvantage of the power screw, that there will be wear and tear, and that is one of the important aspects which we have to take care of in design or in finding out the suitable material. Now, sometimes we want a very small movement, and therefore, we use two threads, one thread here, and on the same screw we have another kind of thread with a different pitch. And if we have two nuts, then you see if the pitch is P1 and P2, and if it is single threaded screw, then of course per revolution this nut moves by amount P1 and this nut moves by amount P2. So therefore, the relative displacement will be P1 minus P2, which could be very, very small. Therefore, it is possible by combining two threads to get a very slow movement, and that is why this screw drives is very useful in getting the slow motions. This mechanism is known as the differential screw mechanism. Differential screw. Now, we may have another kind of screw which, suppose we have thread here, a different thread, but the handedness is different. Now it was right handed, now this is left handed, and if we now have the similar arrangement, here similar arrangement, now whenever this thread, the screw rotates, then it moves either towards each other or away from each other, but then the relative velocity will be, or that is relative displacement will be equal to P1 plus P2. So now it is possible to get a very fast movement. Therefore, by suitable choice of the screw threads, we can have either very slow movement or very fast movement, and this mechanism is known as the compound screw. So this is roughly about the kinematics of the screw. Now we come to the static analysis of the screw force. Now we come to the static analysis. Now here we assume that the screw is rigid in order to find out what are the forces and moments acting on the screw. So we now come to the rigid body mechanics. We consider the example of a screw jack which looks somewhat like this. So this is a fixed nut on which there is a screw. On top of it we have some load. This is used to hoist the automobiles, therefore the automobile weight will come over here, and there is a long handle by which we apply the force and the screw turns, and when it turns it lifts up. So this is the mechanism of a screw jack. Now let us see what are the forces acting on the screw. Now if you draw the free body diagram of the screw, a part will look somewhat like this. If this is right handed, so this is the cross section of the screw, and you will see that this is axisymmetric problem, that is from whatever angle you look like you will see the same. Therefore my exact nature of slantedness is not very important, but what is important that it preserves its right handed nature. Then you see that whenever load is applied, then this side will be in engagement with the nut, only the bottom portion, okay, and the pressure will be on the thread throughout. And if you assume the uniform distribution of the pressure, then of course we can safely assume that the resultant force will act on the mean diameter of the screw, that is the mean of the major diameter and the minor or the chord diameter. Now if you look at the section a little bit closely, then you will see that so this is the part of the thread, this is the center of the screw, and this distance is, let us say, d mean, we consider as d. Now whenever it rotates in that direction, then of course there will be the sliding motions, and because of that the friction force will always oppose the motion and it will act in that direction. The normal force will be again normal to the surface, this is N. Now if you look at this picture, then you will see that the friction force acts here along these directions and the normal force here, whereas this angle is the angle of helix and this is equal to phi. Now if you write down the force balance equation, that is the components of the force along the vertical direction, then you get N cosine phi minus F sin phi, and that is the total upward force, and that must be balanced by this force P. Therefore we have this kind of relationship, and now we use the important fact that the friction force is related to the normal force. Now getting the exact nature of the friction force is very difficult, but we safely use the Coulomb's laws of friction, which says that friction is proportional to N only whenever there is a motion involved, there is a movement already, or it is impending to move, that is the motion is about to begin, only then these two cases we have this relationship. Whereas whenever we have the impending motions, mu is denoted as mu s, whereas in case of the kinetics, then we have mu k, which is the coefficient of frictions, kinetic coefficients of frictions, and usually mu s is a little bit greater than mu k. But for the metal, these are almost same. Now if you use this relationship, then what you get is N equal to P divided by cosine phi minus mu sin phi. So this is the relationship between N and P. Now let us look at the torque. Definitely there is no force along the radial directions, because these two forces are acting on the vertical plane, both of them are acting on the vertical plane, so there is no component along the radial directions. So the circumferential component will be, or the tangential component will be equal to, this is the f tangent, and that will be equal to n sin phi plus f cosine phi. And if you again use the same relationship between f and n, you get n times sin phi plus mu cosine phi. So therefore we get this relation, that is, we have f is equal to or rather p equal to n times sin phi cosine phi plus mu minus mu sin phi minus mu sin phi, and then therefore the torque will be equal to Ft times this d by 2, and that is equal to n d by 2, n d by 2, then we have sin phi plus mu cosine phi. If you use again these two relationship, what you get is the very well known formula, that is equal to T will be equal to P d by 2 times sin phi plus mu cosine phi divided by cosine phi minus mu sin phi. And then if you use the fact that mu, if you write down mu as tan of lambda, which is lambda is the friction angle, then you can write down this as P d by 2 tangent of phi plus lambda. So this is very important relationship, that is the torque we have to apply. This is the torque which we have to apply, that is equal to P d by 2, that is the mean radius of the thread, times tangent of phi plus lambda. Now let us look at the efficiency of this machine. We see that by one turn of the thread, say for one revolution, this weight moves by amount the lead. Therefore the work output will be equal to P times the lead. So this is work output. What is the work input? The work input, we are doing work only by applying torque, and the total work input is T times twice pi only per revolutions. So therefore the efficiency, which is denoted by work output divided by work input, is equal to PL divided by T times twice pi. Again, if you use the same relationship, then you get P, and L you know pi d times dP, that is the pitch diameter, and tangent of the helix angle phi, and divided by, again t is p d by 2 times tangent phi plus lambda times twice pi, which is equal to, now here we make this assumptions that dp is almost equal to d by 2, and this is so for the square thread, and therefore we have the important relationship, that is the efficiency is almost equal to tangent phi divided by tan of phi plus lambda. Now we see that if lambda is increased, again we know that lambda, tangent lambda is nothing but mu. So therefore if mu is increased, lambda is increased, and if lambda is increased, frequency goes down. But what is the relationship between lambda and phi, that is the helix angle, whether there exists any relationship between them, or what is the variation of this efficiency with phi. Let us look at it. Then efficiency is tangent phi divided by tangent phi plus lambda. Let us find out the maximum efficiency. Now for finding out the maximum efficiency, we will have to find out the corresponding phi for which efficiency is maximum, and that is taken by this formula. And what is that? This is sec square phi tan phi plus lambda minus tan phi sec square phi plus lambda divided by tan square phi plus lambda, and that is equal to 0. If you rearrange these terms a little bit, then what you get is cosine phi sin phi equal to cosine phi plus lambda times sin phi plus lambda, and that means that sin 2 phi equal to sin twice phi plus lambda. Therefore we have twice phi plus lambda is equal to pi minus twice phi. Now if you use this relationship, then you get phi max is equal to pi by 4 minus lambda by 2. So therefore the maximum angle, that is angle of helix, for which eta, that is the efficiency achieves its maximum, depends also on the lambda. If the friction is increased, then the maximum value of phi goes little bit down. And what is the maximum efficiency then? Eta max is tangent of phi max, which is equal to pi by 4 minus lambda by 2 and divided by, again, phi plus lambda. Tangent phi plus lambda, if you write down, then this is plus lambda by 2, and that becomes equal to, you can verify that this exactly becomes minus sin lambda divided by 1 plus sin lambda. That is, the maximum value of efficiency goes down with lambda, as you can see from this expressions. Now let us draw roughly the variations of efficiency with phi. Suppose here we draw for various values of phi, and this is, let us say, 0 to pi by 2. it cannot have value more than pi by 2, and here we plot eta, then we see that it becomes somewhat like this. If we, this is for one value of mu. Now if we increase the mu, then the maximum shifts little bit towards left and something like this, and so on. So therefore this is with increasing mu, and for a representative value of mu which is about 0.1 say, then roughly it becomes 0.7. The maximum efficiency becomes 0.7. So therefore now you see the importance of these two things, the helix angle as well as the value of mu, that is the coefficient of friction. Now let us come to the mechanical advantage. Mechanical advantage, as I said, that if you look at the screw a little bit closely, then we need to give a torque T, and this torque is applied by means of a handle. So now here we apply a force P prime, let us say, such that if this length is L, then it gives required torque T. Therefore T is equal to P prime L. And again, if we use this relationship, that is T is d by 2 tangent phi plus lambda, then what we get is P by P prime is equal to will be equal to L twice L by d times tangent phi plus lambda. So therefore if this d is very, very small compared to L, if the handle length is sufficiently long, then we can have very large mechanical advantage. Also this is enhanced by this fact that this value is not very large. So therefore we can have a very large mechanical advantage with the help of the screws. Now let us look at the case when we want to lower this load. How does it affect? Now instead of taking this load up, that is, instead of trying to raise this load, we want to lower this load. In that case what happens? Now again the screw will now rotate in the opposite direction. Okay, screw rotates in the opposite directions, and therefore the friction force will be along that directions. And if you do the same kind of the static analysis, what you get, that if you can get the same, that is the value of the torque required will be equal to P d by 2 tangent, instead of plus lambda we now have minus lambda, because the direction of the friction force has changed now. Now we see one important thing, that is, if phi is greater than lambda, then what happens? Then in that case this is positive. That is, now we have chosen our direction here. So therefore whenever phi is greater than lambda, then we need to give a torque in the same direction in order to lower this. That is, it lowers by itself. And whenever the lambda value is very, very small, that is phi greater than lambda, then it lowers itself. But if lambda value is quite large, then this becomes negative. whenever this becomes negative, that means that we'll have to apply the torque in the opposite direction in order to lower this. That is, if we do not apply the torque, then of course it will stay there forever, and this is the phenomena of the self-locking. That is, it gets locked by itself. So the self-locking occurs only when the is much less compared to, or this is for the overhauling. This is called the overhauling, which is the situation when it comes by its own, and then this is self-locking. Now we can find out very easily that the maximum efficiency for a self or for a overhauling system is we can find out the maximum efficiency for a system which is non self-locking, that is just overhauling, is half. That could be easily found out, and I ask you to derive this at your leisure time. Now I give you two formulas for the sigma, for this eta max, that is the maximum efficiency. One for the case of differential is equal to d1 if there are two threads with diameter d1, that is mean diameter d1 and pitch p1, then this becomes tangent phi 1, where phi 1 is the helix angle of the first thread, and d2 times tangent phi 2 divided by d1 tangent phi 1 plus lambda minus d2 tangent phi 2 plus lambda. And whenever we have eta, so this is for the case of eta differential. Now you can prove this very easily by going to the first principle, that is by balancing the forces and finding out the net torque, etc., etc. And I am not going to derive this here. For the case of compound, compound screws, we have, instead of minus, we have here plus. So these two are the important formula for the compound screw as well as the differential screw. Now here we have talked only of the square thread. Now if the thread is not square, that is it has some thread angle, as for example happens in case of acme or trapezoidal threads, then what happens? Then you see that if you draw this part of the thread, this is slanted, this is slanted this way, then you see the friction force acts again over here. So the direction of friction force is there, but that of the normal force is not entirely on the horizontal, on the vertical plane. So if you draw a vertical plane, it is not here or in that directions, but there will be a tilt with the vertical plane. That is because of the thread angle. Now that will be clear if you draw the same on the thread cross sections. Here suppose this is the cross section of the thread. Here the friction force acts, the direction is towards you, but the direction of the normal force is now not along this, but along this line. So this is the direction of the normal force N, and this makes an angle theta where 2 theta is the thread angle. Now if you do these calculations, then what you get is this form. That is, the torque required now, again assuming the same appliance as the screw jack, but instead of square thread we now have, for example, the acme thread or trapezoidal thread with some thread angle. In that case, this becomes P d by 2, and here we have sine phi cosine theta. The cosine theta comes because of this component, plus mu times cosine phi divided by cosine phi cosine theta minus mu sine phi. You can derive these same expressions if you wish. Now again this becomes again the same d by 2, then this is tangent phi plus mu by cosine theta, and this is mu by cosine theta divided by 1 minus mu by cosine theta times tangent phi. So again, if you denote this by equivalent mu, that is mu dash is equal to mu by cosine theta. Now you see that for the square thread, theta is equal to 0. So therefore mu prime is equal to mu. But whenever theta is non-zero, then this is less than 1. Therefore mu prime is more than mu. Therefore in trapezoidal thread or in acme thread, the coefficient of friction gets a little bit increased because of this thread angle. Now if you denote this by, you denote the equivalent friction angle by lambda prime, where mu prime is equal to 10 lambda prime, then this is equal to, you can write d by 2 tangent phi plus lambda prime. Now here so you have seen the efficiency relationship. Now let us come back to the coefficient of friction. Now in the coefficient of friction we have the friction in power screws. The coefficient of friction here depends on the materials of screws and nuts, then the surface finish or workmanship, then the sliding velocity of the screw, and the lubricant use. Now these are very important, as you can see that the materials of screws and nuts, they are to be chosen properly. The surface finish of the workmanship, this is also very important, and the sliding velocity also it does not depend too much, but also it still depends. And the lubricants used, it is very difficult to use lubricants there, but the machine oils are used there, and whenever such things are used, then we see the coefficient of friction goes little bit down as expected. Now you can use this following table for finding out the mu's for different cases. Here the screw and the nut, you see the screw material could be steel, it may be dry or it may be with machine oil. The nut materials may be steel or brass or bronze or cast iron. Now you see the with the oil, of course mu goes a little bit down, but this depends again on different material. Now there are few special power screws which are used to reduce the friction. One is the screw and rolling friction nut drive. Here instead of the sliding frictions, we sometimes use the rolling friction drive, and that is very efficient because you know the rolling friction is always lesser than the sliding frictions. So then whenever we use rolling frictions, the efficiency goes little bit high, and the load carrying capacity is very large for this case. as well as the backlash error, which is a typical error in power screw, could be removed. We have the second type, which is roller type screw and nut pair. Here the arrangement is very similar to that of the sun planet gear mechanisms. Here, instead of the direct contact between the screw and the nut, it is mediated by a few rollers. Again, the rollers will have threads cut on their surface, and we have less frictions here. The hydrostatically lubricated screws and nuts pair are also very important, are useful. Now, the roller type of screws are manufactured by SKF company in France, and that is very efficient. The efficiency may go as high as up to 0.9. Now, these are very modern type of power screws, and if you want to know more, then you should consult some book. Then here is a small homework problem. Now, here the position of an automobile jack is shown here. This is the automobile jack, is controlled by screw ABC. Here these are the ABC, this is the screw, and it has two-handedness. The screw has nominal diameter 20 millimeter and the acme thread. Both screw and nuts are made of steel. Now, you have to determine the magnitude of the couple to raise the load. Now, you see the nominal diameter is given, but it is acme thread, so you will have to consult the table. The screw and the nut materials are steel, therefore, you have to find out you have to calculate mu, the coefficient of frictions, from the table, and then with the help you will have to determine the magnitude of the couple to raise the load. Now, let us come to the last home assignment, that is in lecture 17. We used a cylinder head of a steam engine, then the pressure is 0.7 megapascal. It was held by 12 bolts. Then soft copper gaskets. If you use the soft copper gaskets, then C value you can take up to 0.4 or 0.5. Then if you use this, then you see that you get, from the calculations, you get the diameter, or the nominal diameter, you get almost 51 point something. Now, if you look up at the table, the IS code IS 42, if you consider IS 4218, then you get the next higher series is 52. Therefore, we can get the screw as the bolt as M52, and this is the safe design of this type of bolt. Now, then we come to the end of this lecture. What we have learned about the efficiencies, how to make the power screw quite better efficient, and we have seen what is the important applications of the screws. With this in mind, we now go to the design of power screw, and that is done in the next lecture, that is in lecture 19. So, thank you.